Okay, good afternoon. Today is December 16th. We like to cover some of the subject which are very important. We could not go through in detail of all the structures other than the laminate which we covered so far. But there are several other subjects which are very important in real application of composites. One of them is the sandwich structures. So far, we mainly discuss about the regular laminate of the plies. But in real structures, a lot of sandwich structure. There are sandwich structures with the core. So today we would like to review why sandwich structures and what kind of cores do we need to use. Well, this is the when we study about the laminate in general, each ply will have information about the material number and its angle theta and number of plies. Well, number of plies is not so critical, but mainly number of ply can be considered as the ply thickness. So mainly what material with what ply angle and what thickness. Now, one of them can be core, and core will have a certain material or angle. Well, in core, this is all core. The top and bottom we have some skin, and the middle between the skins we have a core. Core. The angle of a core doesn't mean anything, not much, because it's a mostly isotropic case. So theta is not so critical, not so important, but not the end or thickness of a core is very critical. So today we like to go through the behavior of the sandwich structures. And then using the high CLT, what kind of behavior we can have. So that is the one subject I like to cover. Okay, well, for example, the layup sequence-wise, we can think of certain plus minus theta, and then we can consider as another one is a core between plus minus theta and plus minus another theta. Okay, we can consider this is a theta 1 and theta 2. Any angle will be okay, but mostly if we consider just the plus minus theta and core and plus minus theta. Okay, in this case, this is core. This is structures called sandwich structures. Then what is this main role of this core? Core, in general, the ply thickness compared to a ply thickness usually 0.1 to 5 millimeters, very standard ply thickness. But the core can be order of the say more than 5 millimeter to even very large, like the 50 or even bigger. I cannot say precise number, but depending on the structures, we can have a very thick core. Okay, so then as you can see that probably from here, the thickness of this ply skin, I would say this is a top skin. sorry, this can be a bottom skin, starting from the bottom to top. So this can be considered as the bottom skin and core and top skin. Okay, so this can be a bottom skin and core and top skin. Okay, well, obviously, mainly because the thick core, the top skin and bottom skin, they are very much apart, the distance. So based on the fundamental mechanics, the bending stiffness of this laminate, we call D. D will be very proportional to this H. I would say this H. H is the this is the H. So this H, order of H, H is square. So if we increase the H, then D will increase a lot, very significantly. So let's take a look at this behavior using our CLT. Actually, if we go to classical laminate theory, maybe this way, we can see that moment is always defined as the stress times Z and dZ. You know what is a stress or what is a Z? This is the definitions. And then sigma, we know that sigma, which is in terms of a stiffness and strain, and we put it there. I'm just trying to remind you that the derivation of a classical laminate theory, and N is the Q is the A matrix and B matrix and B and D matrix. So the moment and curvature relation is the directly related by the Q and the D matrix. D, as you can see, G square. We need to remember that there's a Z square there, and the Q bar. Okay, so if we remember these equations, you know, this ABD matrix derivation and also is a physical meaning is important. Now, if we let's go to here, and then here the D matrix. Okay, let's pay attention to a D. D is the again Q bar and the Z square and DZ. Now the top skin and bottom skin, and this is a core. As you can see, top and bottom skin is very apart, very far, and due to this H. So in this case, Z square, of course, the Z is starting at the center, and this is a Z. Every ply, this skins, plies has the function of Z, but this, I would say, thickness the T, top, and thickness of the bottom, T bottom. The order of the thickness is which is the much larger, T top and T bottom. What does it mean? In this equation, we can say that Z square, I'm sorry, You can say that this is a Z Q bar, and G scale now can be approximately considered as the H scale, and approximately. So integration from all the way from top and bottom. This is the say actually this is a top A matrix and top bottom B matrix. So this is the order, not the precise same, but the A matrix times H scale. Or you can say A times top and half if this thickness is the same, and you can say like that, right? The A matrix of a bottom and H of a something like that. So the it's not precise equation, but I just like to emphasize the order, try to understand the order. So each one, the top skin A matrix is a sort of a tension behavior, and the bottom also tension or compression behavior. And then D is mainly this A matrix and top and bottom times the order of H scale. This is just order. I don't want to drive in detail, but since you have all the derivation and you have a high CLT, you can get the real number. So the this is a D. And main point is that to increase the D, very effectively can be increased by the H. Increasing by H, the top skin, bottom skin, we don't have to add a lot of composite, cost-wise and mass, weight-wise is mainly A and B. Just the core is relatively very cheap and relatively very easy to increase the thickness. So the D can be very effectively increased by the H. H means the core. So what if we, what does it mean? We have we increase the D. Increase the D means that, for the given moment, the curvature or deformation can be reduced. So the bending stiffness is a very important behavior with the structures, and we can reduce the deformation. We can also reduce the stresses. We cannot say exactly reduce the stresses, but certainly structural behavior will be very stiff. Okay, so the now the core, as you can see that. You can see this one. There are a lot of core. You have a honeycomb core, sometimes a wood. Here we shows that wind turbine blade, even wind turbine blade, all the skin is it is a sandwich structure, so top and bottom. Just in this skin, top skin and bottom skin, we have a composites, and then a lot of core. This is a effective way to reduce the total weight, and a very effective way of increasing bending stiffness. Okay, so let's take a look at and now try to run the CLT. Again, detailed equation and derivation, you can do it step by step. But the more important point is that you understand the concept. And sometimes you may confused by the effect of a core. This is a core, and this is a composites, and this is a core. And if this is a from top and bottom is all made of the composites. Okay, made of composite. Okay, made of all the plies like this. Then this will be the stiffness will be order of H the cubic, and this is the D equal H like this. Because Z, when we integrate, this will be no longer constant on the right-hand side. Then is integration giving us the H cube. But still, as you can see with the core, the stiffness will increase the with respect to the H scale, which is the still a lot effective. Basically, actually, this way, the mass will be very heavy, right? Mass will be very heavy, but this one, the core, the density of a core, density of the core is very small compared to a composite. And besides, as you can see, if we like to have this much same thickness of the total laminate, you can imagine how much the cost it will be very costly, and then the weight will be a lot increase. So again, the core, the density is very low, and the prices are relatively very cheap, and still the structurally, the bending stiffness is a lot increased, very effective of increasing the stiffness, bending stiffness. Okay. Now, as I mentioned last time, last class, you should have your own version of the high CLT ready in front of computers. Okay, let me. Okay, this is the CLT which I distribute to you. And okay, here is the main CLT. Now, we just go through, review the core sandwich. Now let's take a look at how to enter, how to do analyze the sandwich structures. So this is again the ply layout, first to 8 layer. And as you can see, each ply will have a same composite, and material number is 4. Material number is 4 means that if we go here, and the material number 4 is this one. Now, what we like to do, according to our derivation, very simple derivation, we like to enter some core, say between here. How do we do that? Well, you can simply just now, if we like to enter the core, total number will be the 8. I mean the 9, right? 9. So now this center one, now this will be as the core. So let's define this one as the core. Let's try to distinguish like this. And then what you need to do is that we need to choose the core material. So to do so, we need to define a core here. Let's see if there is any core. There is a core there. So core number is a 17. And now please pay attention to the stiffness of the core. So 0.1 gigapascal, but as you can see, compared to others, very small. This is a real stiffness. 0.1 giga means 100 megapascal. And as you can see here, say typical stiffness of the core, say I need to say the structures. Or wind turbine blade. Okay. There is not much. Let's see. There is a balsa. Balsa is the wood, natural wood. It has a stiffness. But what I like to show is that the stiffness of a core is not so important at all, because compared to others, that stiffness can be negligible. Just like to show you a real material property. Okay, this can be good data. And as you can see here, as we just studied that the role of the core is that is a very light, and also we just saw. Okay, here. See, this is the density, okay, density and the stiffness, and density and stiffness, as you can see, Well, depending on how we make the core, the stiffness will vary. Stiffness will have a E1 and E2 and E3. That's not so important. But as you can see, this is order of the 0.1 order, Young's modulus. And then density is the order of the 200 kilogram per square meters. So as you can see, how light and how low stiffness it is. Okay, so so you can see that 0.1 is the not a strange number. This is it can be one of the real values. And also, well, Poisson's ratio still regular one is okay, and then strength is also not so important, and etc. So anyhow, we choose the core 17, and here we choose the 17, and then the thickness 0.1 to 5. Now let's try to choose the thickness. So this is the 0.1 millimeter and 0.1 millimeter. Now we like to see that this one is like 50 millimeter. Okay, so and then let's apply certain load. Say bending moment, because the bending moment is the most critical one. And let's directly go to our output. As you can see that. Okay. Well, just arrange them side by side. This is the result, and this is the layup sequence. Okay, what I like to show is that depending on this thickness, let's start from the 1, and as you can see, there are I'm sorry, we have to choose the 1. Okay. As you can see, there are top and the bottom, then the middle. From here to there, this is the core and top skin and bottom skin. And this is the sigma 1 and sigma 2 and shear. There is a slightly shear because this is not perfectly not perfectly symmetric. As you can see, yeah, this is not perfectly symmetric. This is the minus 45, and okay, this has to be 45, and this has to be minus 45, and this has to be 45. If the total is not quite symmetric, there is always a coupling term. Coupling term, the behavior become very complicated. I'm not saying we have to avoid that coupling term, but just for the purpose of a better understanding, let's just consider the symmetric. So now it's a perfectly symmetric, right? And then we have a core. A core, the angle, I would like to show you. Okay, as you this angle is not a big deal. Uh, Strange. Why this stiffness? Uh, Okay, let's go to 17, the core. My point is that the angle of the core should not affect the overall stiffness behavior, but who's familiar? Okay, D21. I'm sorry, this Poisson's ratio has to be this guy. I don't know why this formula is wrong. This is the one Poisson's ratio, right? This is the Young's modulus divided by 2, and the 1 plus mu. F21 is the Poisson's Poisson's ratio. So this has to be sure. Okay, well, so now this core should be precisely isotropic. But actually, the reason we have a slight shear is that not because of that one. You see, you still have a shear. The reason is this okay. I need to correct my statement because this one is still bending. Okay, bending. So this is a symmetric, but the bending, since with respect to this guy, this minus, how come it's changing? Oh, I need to, sorry. I need to enter the 45 minus 45 and 45 minus 45. Right? Okay. Sorry, there was a formula. So let's double check. Uh, there is a slight the shear term due to this bending, even though this is symmetric, because the bending will, a moment will cause okay, well, look at this top skin. Okay, top skin will subject to a compression, and compression, then this extraction, one direction and two direction, we have a certain stresses, and there is a certain the shear, slight shear there. Yeah, yes, right. I mean, shear can be generated because it's under compression. That's right. And even the bottom one is the same thing. The reason is this one is a top skin, and this one is the say okay, this is the bottom skin, and this is the top skin, right? Okay, so let's say this makes the okay, this is a little bit tricky one. 45 minus 45 and 45 and minus 45, and then this can be 45 and then minus 45. And this one is, it doesn't matter. Now, as you can see, now all shear is a 0. Okay, all shear is a 0. Well, this one, I'm gonna just copy this. I have trouble with my mouse. Okay, here. And then, as you can see, that the output, the stress now shear stress will disappear completely, right? Well, this is not the main point I wanted to emphasize, but since just for the purpose of a better understanding of a composite, this is the another point. Okay. Situation is this. So we have a top skin and core and the bottom skin. So now this one has the structures and subject to a bending. And bending means that this is the compression and this is the tension. Okay, this is the compression and this is the tension. So if we look at the only this laminate, okay, only this laminate, and take a look at this one. This one itself, we have only 4 plies. This 1, 2, 3, 4, and this. I'm sorry. This is a 1, 2, 3, 4, and this is the 6, 7, 8, 9. So this one can be is 1, 2, 3, 4, and under compression to eliminate the shear. This has to be itself the symmetric. See, this is a minus 45, minus 45, and 45 and 45. So this one on the compression, this is a well balanced, and this is a well balanced. It doesn't cause any much the shear deformation. So now the shear stress will disappear. Well, we don't mean to just eliminate the shear stress, but for the purpose of understanding of this structural behavior, why the shear stress can be 0, why sometimes the shear stress is generated. That's what I like to explain. Okay, here is also, this is a symmetric with respect to this top laminate. As you can see here, this is a symmetric, and this is the right. This is a symmetric. So in this case, the under compression, there will be a no shear stress occur. But if this is the 45 and the minus 45 and 45 and minus 45, and this is not a symmetry, right? If you look at it, then there is some shear stress will generate. Let's go back to that one again one more time. So let's say 45, 45, and then this way, and minus 45, and see, this one can be sometimes we can make the mistake, non-mistake. We cannot. We may not be able to catch the Y shear stresses. Again, you just consider, oh, this is symmetric. Minus 45, minus 45, and looks symmetric, and everything is okay. And then on the bending, and now how about the shear stress? Now you can see that there is a slight shear stress. Now we understand why there can be a shear stress. Right? Okay. So I don't want to spend too much time. I already explained. I just want to make sure that this can be any structure understanding of the core. Each scan may have its own symmetry. Okay, this that can be an important point. Okay, so there can be a slight shear stress. Sigma 6 is not a 0, and this is a sigma 6 is a 0. This is a 0, and because of this one itself, okay, this is a itself with respect to here is a not symmetric, and this one is also not symmetric. So in this case, the with respect to this core, overall symmetric is not the point. Okay. Most important point is that now you are able to enter the layup sequence and the and structural behavior. Let's take a look at, let's try to use the effect of this thickness, okay? We don't change any layup sequence. Okay, let's get back to this one as minus 45 and plus 45. And then this can be 45. minus 45 and minus 45 and 45. Okay. Now, what we like to do is that we like to understand the effect of a core. So let's consider this one as the variable input in the quick chart. Okay, in the quick chart, this is the input. And now this, let's say, sandwich, I would say 1. And then this one, you can just consider as the D, or you can consider how much the curvature it may generate. Okay, okay. So let's say D11 and the curvature 1. Let's consider these two. So D11 comes from where? D11 comes from here, ABD matrix, and D11 is this guy. And curvature 1, where is the curvature 1? Curvature 1 is the this guy. Oops. So curvature 1, oops, equal curvature 1. So curvature 1 response. Well, other curvature 2 and other behavior will be pretty much the same. Just like to understand the now input. Input is the what? Input is the input is the in this case this is the core thickness. Okay, this is the core thickness. Okay, so let's the core thickness. Let's say start from 1 millimeter. Okay, and then 10 millimeter, and step value will be 0.5. Okay. Okay, so XX is the thickness. So this guy is the core thickness. Well, the core thickness, and this one is also core thickness. X-axis is core thickness. As a vertical is the curvature. And as you can see, D is the increasing, is like the second order polynomial, right? That is the behavior we observed, that this is a D, is a H square, the parabolic increase. Since this parabolic increase, the same moment and curvature will be 1 over square. So that will be behavior like this. So as you can see here, how effective the core thickness. The density will be very low. We don't have to calculate, but from here you can see that how effective it is. Okay. that actually this still is a part of a classical laminate theory, but I like to emphasize again how importance of this core, very widely used in composite structures. This is one important point. Let's see. Yeah, as you can see here, this is the sigma O-axis and the on-axis strain, as you can see. Right? In the core, there is no stresses, and of course the core, there will be strain will be always exist, but stiffness is very low. That's why the almost zero stress. Okay, that is the one we need to clearly understand that. And the Xi-U, the Xi-U is very small. Well, this is mainly because of a very low moment. But the important point is that this distribution. And another point we like to understand is that top and bottom is the skin is exactly same, symmetric and etc. But the Xi-U failure criterion can be different. Why is that? Xi-U failure criterion, top and bottom skin can be different. Why? The reason is that top and bottom will subject to a different load. One is the tension, and the other one will be the compression. Okay, so the top skin and bottom skin, as you can see, again, if we go to here, the stress, okay, strain or stress, one axis, one is the one we apply the load, and the stress will be tension, and on the top, and the bottom is a compression, right? And compression, and of course, it's very important to notice that, pay attention to the this is the sigma 1, and this is a sigma 1, which makes the bending moment. And now this red is the sigma 2. Why is 0 and 0? Because we didn't apply the bending moment in two directions. And here, we didn't apply shear load twisting moment, but this is the tension compression, and the resultant will disappear. So even though there is the Parsons effect like that, this Parsons effect is not caused by the load. This Parsons effect of the strain in contraction is caused by this tension. But as you can see, the load-wise is 0. It's very important to note that. And that's why the tension, same laminate, but tensile strength will be different from a compression strength. That's why Xi-U and top and bottom skin, we have a different values. Okay. Well, what we cover right now is the it's just a matter of understanding. To get all these values, you can enter and you can use this CLT. You can enter the value, and then you can understand the behavior. Okay, it is a 1:34. Now let's take let's have about the 10-minute break. Okay, 10-minute break. Let's come back to 1:45. 1:45. Let's continue to our class. And then after another about the 1 hour class, and then we will have a 1 hour break, and then we will have a final exam today. Okay. So see you soon. Okay, let's continue. Please, in the cutoff, enter your name and your student ID number as I announced. Okay, well, one last subject I'd like to review for you to better understand composite is the micromechanics. What is the concept of micromechanics, and why is it important, and so on. Okay, I will just go quickly review. Just like to emphasize the importance of this subject. If you need a further information, now you understand the importance of this subject. You can search in the internet very easily. So just go through a detail about the micromechanics is not my intention. My intention is that there is a subject called micromechanics, and then you can always go to visit, and then you can further study in detail, such as the micro mechanics of composites. This is a very general statement, and then you can see hundreds of thousands of references you can find. So the micromechanics can help reduce the number of tests needed to characterize the composites. And when we develop the different types of composites, well, we can use this micromechanics. So just to understand the importance of micromechanics, and then you need to again use this one to understand, for example, thermoset composite, thermoplastic, or metal composites, and different fibers, and estimate the strengths, and so on. And also Abacus, ANSYS, they have such a we can use the conventional CA tools to go more in detail, and there can be a lot of YouTube and study. Okay, so again, I don't need to go in detail, but I just like to emphasize that we have this is an important subject. So well, in understanding of the micromechanics, so we often use this kind of figure, pyramid figures, starting from the bottom, micromechanics, fiber, and the interface and resin, which makes the unicell. And now unicell, a repeater of this unicell, can now make the one ply, and then a laminate. We have a composite laminate, and then a structure. This is the hierarchical structures of composites. So this is the important. Okay, so very similar point is that, you know, the real structures can be a wind turbine blade, can be a airplane, can be a pressure vessel, any composite structures. Now we have this is a macro scale. We have a local, we call a mesoscale. Mesoscale is the order of the toe, each toe, and oven, because each toe now has the 20,000 fiber. So let's go more in detail, more in deeply. Then we have a micro scale where we have a fiber and resin system. Now fiber is the order of the 7 micrometers or 10, and here is the order of millimeters. Now, each in the micro scale, we have a fiber and resin and interface. We have its own constitutions, or sometimes SN curve. Then the material may degrade in the resin or fiber and interface. And then once this damage accumulate or degrade or propagate, there will be a certain level of damage distribution. So we can homogenize them, or go in detail is a really complicated behavior, but we can think of the damage homogenization, and of course the effective stiffness will degrade. For example, under a lot of fatigue load, the stiffness will degrade, overall stiffness, and then we can get a effective stiffness, and then this will change the structural behavior. So this is one example, but again, the conceptual understanding of real behavior of the composite is a result of the behavior of the micro levels, like the fiber and resin system, and its degradations. So you have seen this figure many times. This is the toe or bobbin. One toe has the 20,000 fiber, or 24K fibers, and this can be used to make the pressure vessels or woven fabrics, many structures. Or you can stitch them like this, because we want to hold them. How can we hold each toe? This is each toe. Now we need to layer them without resin. Without resin, how can we make the laminate or lamina? Well, there is a way to stitch them. Is the as you can see, there is no resin here, so we need a warp yarn. Yarn is the very yarn to hold them. It is a stitching. You see the zigzag stitching. So that yarn is the not as a structural yarn, but just for the purpose of holding the toes. Okay. So anyhow, so point is that if we look at the microstructure, say each ply has a 0.1 to 5 millimeter, then this is the real fiber arrangement, as close as a real one. And the point is that 0.125 millimeter thick, and each one has the fiber has the diameter is like the 7 micrometer, and then you understand how many fibers can be stacked to make this 0.125. You can count them, right? So you can see that about the 20 fibers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 20 fibers will make the 1.15 thick. This is a very typical pre-preg, and pre-preg is this guy, this one, and then you layer, and make the structures. As we just reviewed, we can make the core as a sandwich. This is a very typical structural behavior on the structures for the aerospace. Now, this is a real photo of the real fiber arrangement, but to model them, to understand the behavior, we need a sort of a model to arrange the fiber. So this kind of arrange is called a square array, or hexagonal array, or diamond array. So this is the one just for the purpose of a theoretical derivation, and then this way, or sometimes just the fiber and resin system, or sometimes rather than circle. Circle is very complicated mathematically, so you use the octahedral OFM fiber, octahedral fiber mix arrangement. So with this, we can drive all the analytical solution on the transverse load and the shear load. And you can use the FEM, like the Abacus and the ANSYS, to arrange the fiber and resin system. So anyhow, once you arrange model them, you can come up with this, or you can just directly model the random fibers. Is also one choice. So you can have a sort of steps. The main point of this flow is that the ply will subject to a transverse of very different load. Now, what will happen to each fiber and resin system? That's the main point. I will just go through, skip the detail. But one thing I like to, for example, this is the transverse load. The sigma y. We often consider sigma y and sigma 1 and etc. Now, sigma y, which will cause the stress distribution inside the resin and fiber. This color shows all the sigma 1 color, sigma 2, and etc. As you can see that there can be a lot of different stresses may exist. And then this is the one very interesting observation, is that just a transverse load, okay, transverse load, and the resin strength, TM, we call TM. What is a resin strength? Resin strength is about 50 megapascal or sometimes 100 megapascal. Now, transverse wise is the composite transverse tensile strength. Theoretically, we can obtain that 64% of the matrix strength. Why? Because there are stress concentrations. Imagine that we have an inclusion which will cause the stress concentration, and then this stress concentration, because of that, stress will be high, and then the matrix will fail earlier than just a pure matrix. So to make the long story short, the transverse composite strength is only 64% of the resin tensile strength. Okay, so this is important to understand that. And now, how about the compression? Compression, well, this one, the composite strength is about 2.7 times higher than tensile. Of course, we have we assume that beta is 1.8, means that tension and compression matrix strength has a certain ratio. But just to understand the behavior, and the also interface microstress is important. Under tension, the stress along, between the interface, always a normal stress and the shear stress, right? And also another shear stress along the fiber. So this shear stress and normal stress and we can obtain from FEM. So as you can see, transverse, you can see the shear stress can be higher at a certain degree, like the 30 degree. The shear stress, because the shear stress will let's say this is a tension, right? This is a tension. So there will be no shear. There will be no shear because of a symmetric. But about here, we will have a sort of a shear stress like this. So you can imagine that. So depending on the glass and carbon, and we have a different shear stress at the interface. It is often very important to understand the interface stress between the fiber and resin system. And different, say, fiber and resin stiffness difference and fiber volume fraction. As you can see, a lot of stress distribution can be generated. And also, all the stress distributions are too many to consider. So sometimes we just consider this a certain point, which are mainly major point. So we usually check the failure or strength at this sometimes a 19 point, sometimes a 20 point. We can select them. So this is how we get the effective stress, and again we can assume this regular array, but also we can consider random. While numerical we can generate a random for the given fiber volume fraction, like a 60%. So this is the real photo, and this sample 1 to 3 is the just the numerical image generation using this kind of algorithm. So it looks similar. Microscopically they're different, but overall the fiber volume fraction 60% is the same. And then we applied the transverse load, and then we got all the stress distribution and checked between the fiber and resin system, and then we plot them stresses, maximum normal stress and maximum shear stress. And this is the from a computer random generation, and this is a real image. Real image, you just import this into a abacus, and then we can mesh them. We can get the stress. As you can see, this range of stress, the range of distribution is really similar. So this study is very useful, just a numerical simulation. So using this kind of a random generation, we can understand the resin failure and fiber failure, and even fatigue, and effect of the fiber volume fractions, and we can do a lot. And again, the main purpose of advantage of this micromechanics is that now, rather than performing all the tasks of the UD or composite, we just all you need to do is to understand the resin and composite. We can estimate the composites property, and we can also have a certain statistical distributions. all the material property, even geometry or even the fiber diameter can be probabilistic. I mean, it has a probabilistic distribution. So whatever we can assume distribution like that, and then through this micromechanics study, the ply level stress or stiffness can be the sort of probabilistic distribution. This can be obtained. So so we have a certain distributions of the Weber distribution for the failure. We should be, or we may be able to predict even these kind of distributions. Okay, well, there is a paper you can refer to understand this model, OFM. OFM is nothing but the fiber arrangement models so that we can drive the analytical equations. As you can see, this is the you know, the stress and strain compatibility and quantification we can precisely obtain. Now look at this stress concentration. This can be defined in terms of constituent material property, resin property, and fiber volume fraction, etc. This is very useful to drive the stress concentrations. And EM star is the ratio between the Young's modulus of a resin and the fiber stiffness. And A is the given in terms of a fiber volume fraction. So again, this M is nothing but the stress concentration, how much stress is concentrate. And imagine this can be just obtained the analytically. It's so powerful, can be so powerful. Anyhow, and using this one, this is the Zayu or whatever failure criterion. So this is the X and Y. This is a failure criterion. And then we can consider another axis is a shear stress. So this is the also obtained. And once we have another big advantage is to understand the cyclic load and fatigue load and creep behavior and the viscoelastic behavior as well. So we can we can understand a lot details using the micromechanics. Okay, so again, I just want to bring this issue so that whatever research you do, you can always find relevant references from internet, and then you can further study. Well, this is the same subject. Okay, that's the brief cover of the micromechanics. Now I feel that we mostly cover what we like to cover in this course. Okay, composite. Well, composite is pretty much wide. The subject, material-wise and mechanics-wise, structure-wise, it's a very wide subject. But once you understand the composite structures, composite materials, you should be able to do a lot. You know, I can emphasize that these days, manufacturing of a structure, manufacturing of the automotive, I'm talking about the structures, or wind turbine blade, or pipe, you name it, or the constructions or bridges, and so much the structures And now we need to optimize the structures. Optimize means we like to make them light, and we like to make them cheaper. Now, what can we do? Well, if we don't know about the composite, we just use the steel or aluminum. Well, that's very limited. So if you make yourself as the composite engineer, you will be have a lots of opportunity for your career. So the understanding of composite structures is, I mean, it can enhance your career. Now, see the difficulty. Sometimes many, even company, even individually, they are saying that, oh, composite structure is difficult. And a lot of company came to and look for engineer, a composite engineer, but they cannot find composite engineers. The main reason is that composite engineers, you need to understand the material behavior. Okay, material behavior. I always emphasize this one. Material behavior, you should know the how to design or say based on the simulations. And third, you need to understand the manufacturing process. We, as a mechanical engineer, we mainly concentrate on, the CAD and CAE, and this sounds familiar to us. But just the design or simulation is not all. Without understanding manufacturing process, without understanding material behavior, we cannot design properly. So the composite engineer, we need to pay attention to understanding material behavior, resin, and the fiber, and even sometimes the sizing between on the fibers. So material behavior is important. And mathematically, we need to understand the anisotropic behavior, or plasticity, or viscoelasticity, and etc. So material behavior, especially polymer. Polymer has a very typical behavior, and we have to have a rooms for understanding. One is the material. What kind of resin we can choose from, and how much is that? And then, there are a lot of different fibers coming out on the market, and then how we can choose and design. Well, we need to understand the anisotropic and the laminate and failure envelope and the fatigue and the buckling and the natural frequencies. You need to understand the structural behavior. Structural behavior is so important. It's not just the composite, okay? We have to understand the structural behavior. What does it mean, structures? Structure, we have a very typical, the characteristics is the bending or shell and plate, and buckling or failure criterion, and the natural frequencies, and so on. We have to understand that. Now, manufacturing process, again, we cover the infusions and all the filament winding and RTM, and so much different manufacturing process of a composite. or draping. So manufacturing process, without understanding manufacturing process, design it has no meaning. And without understanding material behavior, it has no meaning. So we as a composite engineer, please keep that in mind. We have to combine them all, okay? It is the this is actually the message I like to convey to you, and then so that whenever you come to a situation that you need to manufacturing process, you have to really understand manufacturing procedure is basically the temperatures and pressure is as a function of time. How can we apply the temperature? How can we apply the pressure as a function of time? That is the manufacturing basically process. Of course, depending on the geometry. You know, what kind of a geometry we like to manufacture. Is a pressure vessel type, or a pipe type, or just a flat, or a rib. You know, so much the situations. And of course, we have many different layers and etc. So from time to time, really, you can train yourself or make yourself familiar with these three subjects: material and design and manufacturing process. Then, if you are able to call yourself as a composite engineer, now you can, you know, make yourself is very competitive. So you can choose any job you like to choose, rather than you just being, you know, chosen by the company. You can choose what you like to do if you are a good composite engineers. Okay. Okay, I cannot emphasize enough how important the concept of these three concepts. Okay. Now I like to go a little bit more detail about the procedures in composites. Well, a little bit theoretical touch, as I mentioned. The always the inside the material, not just the composite, inside the material, we always have to have a stress strain constitution or stress strain relation, or now you can say stress strain temperature. So simply you can say strain and you know, the compliance and the sigma and plus the CTE. You need to understand this concept, the stress and strain and the temperature relations. Is always we have to have it. Now this composite makes this one is a more generic and anisotropic. Now this is a stress strain relations and temperature relations. And now next one is the equilibrium. Force equilibrium. Force equilibrium, simply, I like to just use the tensor equations and the certain gravity. And then, well, if you're not familiar with the tensor, well, you don't have to fully understand, but you just roughly get an idea that, okay, stress distribution, variation, comma is a variation of a stress inside, has a certain relation with the dynamics of the structures, composites. So the equilibrium equation is important. And then constraint. constraint means that, you know, the geometry has to have a certain constraint in deformation and etc. In terms of mathematics, this is the called epsilon ij, and displacement and strain relations. This is the okay. Well, linear relation, we have this. Okay, so yeah, it's a very theoretical expression. But now this 3 point is the all about the mechanics, okay, or elasticity. You heard many times elasticity, right? Elasticity. What is elasticity versus structures? As a big, not big difference. The principle is the same, but the elasticity is that, you know, the displacement and the strain and stress. Those are three. So the displacement is a 3 field. The stress with a 6 component, and the strain is a 6 component, right? So totally how many? 12 and 15. Now equation, this is the 6 equation, and this is the equilibrium, and UI, this is a 6 equation, 3 equation, and now strain displaced, so this is a 6. So as you can see, this is a 15 equal 15. So 15 equation and 15 variable to solve, that is the elasticity. So we have to deeply understand all each, and then things like that. And then of course you can use the finite element method to understand or to get the all the boundary conditions and the boundary conditions. All you need to do is the boundary conditions, and then you specify this material property. That's it. Of course, the geometry, right? Geometry. So always when you solve the FEM or whatever, make sure you got the right geometry. Make sure you have a right boundary condition. Boundary condition can be a displacement or a force, 2 types, and then a material property. Always 3 concepts: geometry, boundary condition, and material property. So make sure you got all the right property specified in defining problems. And then rest of it means that, you know, equation this and in force equilibrium and this one will be taken care of by the FEM, all the energy equation, etc. So this is again elasticity. Now I like to say structures. Structure is mainly over here. When we design, while we don't go deeply about the elasticity, we just understand the structure, and this is the design. Now, structural behavior, I like to emphasize that failure criterion and buckling and natural frequency. Okay, always a 3 concept, and failure criterion and buckling and natural frequency. Now, if it is the failure criterion for the static, and then dynamic, we have a fatigue. Okay, so fatigue, static failure criterion, and buckling and natural frequency. That is the structural concept. Structure, we don't consider each detail, but the structure we consider as the resultant. Resultant means that, you know, the moment equal, rather than stress, we just consider this stress resultant, so that we can, we don't have to consider detail about this stress. We just consider a resultant moment, a resultant in plane, and so on. So elasticity is a micro level. I would say structure is a sort of a macro level. You can simplify the analysis. So you need to understand the clear difference between the elasticity and structures. Again, the structure, when you design, you have to understand the failure criterion, buckling, and natural frequencies, and fatigue. Using the CAD. Why you need a CAD? Well, CAD, you need to specify the geometry, right? And the boundary condition, you need to apply to all the load and the material properties and so on. And the manufacturing procedures is, again, yes. Well, each one we can spend, the almost 1 year or 1 semester for fatigue or failure criterion, buckling, and natural frequency. But we have to train ourselves and make ourselves, remind of each subject from time to time. Otherwise, we often forget the importance of each subject. Okay, so what we cover so far in this class is that we review the manufacturing procedures. Not much, but we cover the infusion. Basically, the manufacturing procedure means that resin and fiber, how can we combine them? How can we impregnate fiber into resin system by proper temperature or proper pressure, and that is the concept of manufacturing procedures. We went through infusions, but other procedure will be the same, either RTM or filament winding. All matter is the how to impregnate fiber into a resin system. Okay, so again, what we have covered was the to get into a structural behavior. We wanted to define the moment of the structures. Okay, material behavior, fiber and resin system, and then well. Even though I emphasize this all the each one, I just like to help you to understand the overall behavior. But each one of you have a different background, your technical background, engineering background. You have to have your own versions of understanding. So. You need to write down from bottom to top and every subject and how they are related and so on. You need to have your own version of understanding. To do so, you have to see it and you have to think and you have to write down. And then whenever you need to refer to a certain subject, you have to you have all the information from the internet. Again, this is not just a simple procedure. So you have to train yourself over and over and make yourself familiar with this each subject. Then you can, someday, good composite engineers. Really, I like to tell you that the not just in Korea but all over the world, we are very short of a composite engineer. Really, all over the world, they are look for the composite engineers. They cannot find the composite engineers who can design or manufacture and things like that. So that was actually the main purpose of this class. I like to bring all the issue. I don't mean to just go detail. Why? Because detailed information can be always found from internet. But what kind of subject we have to understood and then what kind of application we can think of. Okay, this is the last review of composites. Okay. Well, I understand that you are in mainly the concern about the exam in 1 hour. The exam will start 1 hour, and then I will assign the exam and library assign, and then you solve them. And then you will have about 1.5 hours to solve them. The reason I'm taking this type of exam is very similar to a real case. Real case means that you as an engineer, either in company or in the project, you always have a given problem and you have to solve them quickly. Well, so but I just like to give you some subject is that the high CLT. As you can see, high CLT can be one of the most effective tools for you can try to understand, to calculate the behavior of the composites. And the CLT, of course, you can have choose all the materials. You can choose the materials and the layup, and angles and things like that. And you can apply the load. Right, and the layup you can have a core sandwich structure, and the load you can also consider the thermal load, right? So this is a given, and then you can have the stresses or deformations. Deformation means that in-plane strain. And curvature. And once you have a stresses, you will have a failure criteria. You will have a failure or not. You can decide that, right? So as you can see, this is the power. So you can do some parametric study. Parametric study using the quick chart. And of course, you can hear, I didn't mention much, but you can have a infusion procedure as well. And you can perform the parametric study very effectively using the quick chart. Of course, between here, you can have a ABD matrix. And you can perform the parametric study. Well, so in today's class, I mean the exam, you can the problem will be specified a certain loading case or a certain layup case, and you can have a failure criterion values, not just the failure criterion, but the maximum strain or maximum the stress or strain can be also considered as one of the failure criterion. Okay, and of course you can choose the material layouts, the material property, or carbon, and the thickness, etc. Now, any question about the this type of question about the CLT? You can type in your cutoff. Okay, well, you can consider many. Oh man, we'll start again. Oh, man. Yeah, sometimes it's applications like the pressure vessel or some bending and etc. And then okay, well, it is a 2:40. Let's get back to 3:30, and then I will assign, and then you will do yourself. Okay, independent is important. Independent. No discussion. Okay, no discussion. It has to be independent. You have to solve it by yourself. If you have any question, freely ask me. I will answer as much as I can. So let's get back to three. I'm gonna type 3:30 p.m. Okay. Thank you so much. And then this will be an official close of this whole one semester of advanced composites. Anyhow, see you in 50 minutes for your final exam.